Hi and welcome to a new episode about digital audio mixing with FPGAs. In the last episodes I already showed how to decode the Behringer UltraNet protocol with this Wider 4000 here, or how to build a fully digital Class-D amplifier with a custom Sigma Delta converter. I had a lot of fun with both and I thought about what else could I do with this kind of technology. Thankfully, you wrote some comments on the last videos and also sent me some emails. The question came up several times as to whether the Wider 4000 could also be used to decode AES-50. AES-50 or SuperMac also uses Cat5 cables and is based on OSI layer 1, but decoding is more difficult as the data rate is much higher than with UltraNet. Maybe I will take a look at this at some other point. But one other thing has piqued my interest. Several years ago an April joke about a new Behringer X32 with doubled number of channels, so an X64, gave me another idea. As a trumpet player in a big band since 1994, I have often been confronted with a high audio channel demand, and a special feature of a big band is the high number of individual audio sources that can be picked up. 32 channels are quickly used up here, and the X32 has another very interesting interface in addition to UltraNet and AES-50, the expansion slot. First, I'd like to introduce my today's sponsor, me. I make these videos completely independently and without any intention of profit. All devices are bought by me and I have no relation to the individual companies. If you like the videos, I would be happy about a subscription or a few comments from you down below. And thank you very much for the 4000 of you who already subscribe to this channel. Good to know that this kind of very special content is interesting for some people. A typical lineup of a big band consists of 5 saxophones, 4 trumpets, 4 trombones, bass, guitar, piano, drums, rhythm and so on, vocals of course, and with a moderation microphone we have the full 32 channels already used. But sometimes we have more saxophones or trombones on board. Now it would be great if we have more processing channels available. Since we can send and receive 32 channels to and from the expansion slot, this would be a great addition. Of course, Behringer released their new Wing console with 48 channels a few years ago, but I now have my X32 that I'd like to use a bit longer. Well, there are already many cards for the expansion slot and also offer additional mixing options. The original XUF with USB and Firewire, the XUSB, the XLive, XDante, X-ADAT and so on, and also a non-official one from Schematics, the U-Track32. So if Schematics can develop such an expansion card without any official connection to Behringer, then it must also be possible with a DIY project, right? What do we actually have to do now so that we can develop our own card? I have absolutely no information about the expansion slot or the protocol used here. So there are now 4 steps to do. The first one, some rough reverse engineering of an existing card. The second one, reverse engineering of the protocol used here. The third one, create a circuit diagram with our Wider 4000 of course. And number 4, construction of a board and some tests. First of all, we need to find out what connections are used. Unfortunately, on the cards there is no designation or more information about the used socket here. So the first attempt is to do a Google image search, and after a long search I found a promising result at JAE. From the dimensions and the illustrations in the datasheet, this connection should fit. At least we should now be able to physically connect to the X32. Now it's time for the basic connections. The simplest card would probably have been the X-ADAT, but I don't have that here. So let's take a look at my XLive card. There are 2 XMOS ICs on the board, as well as an STM32 controller. This is a great sign that we can use a moderate microcontroller for communication, as the STM32 is a Cortex M-type controller. So I first sketched a rough circuit diagram on a paper. We know that the expansion card supports 38 channels in blocks of 8. And there are a total of 6 lines between one of the XMOS and the connector plug. Presumably, 4 of them are a I2S-like connection plus the necessary bit clock and frame sync clock, hopefully. I2S actually only supports 2 channels, but UltraNet had already transmitted 8 channels here. In addition to I2S, there is also TDM, which officially supports more than 2 channels, so it makes sense to start with TDM here. As we can decode the signals later in the FPGA, we are not making a big mistake here if we are dealing with other types of signals if my assumption is wrong. After a few hours, I came to the following conclusion. The X-Live consists of 2 XMOS, a U1169 with USB connection and an XMOS L1169 without USB. There's also a small STM32F091 microcontroller for communication between the 2 chips and the X32. A 512 megabit SDRAM chip and a standard SN74 octal buffer logic IC seem to buffer some signals here. A total of 6 lines run from the board connector to both XMOS chips. As I said, presumably 4 times TDM and the 2 control lines for bit clock and the frame sync. Then 4 additional lines run from the XMOS without USB connection to the SN74 logic IC and from this back to the board connector. Maybe 4 TDM for return channel back to the X32? We'll see. The XMOS with USB connection is then also connected to the logic IC. Obviously, this allows the X-Live to be easily switched between USB audio and the SD card audio. There are then 2 more lines between the board connector and the STM32 controller. This is probably a kind of control connection, hopefully something like I2C or UART. And we actually only need a fraction of this for our new DIY system. Just the 2 control lines and the TDM lines. I planned to use an SD card connected via SPI to playback some MP3 files and host a web server for controlling this whole system. If you look at the datasheet of the XMOS chips, they are pure 3.3 volt chips, so we don't need any kind of level shiftings for the lines. This already gives us a very good overview of the overall system. For the actual board, we still need a plan of how the WiDAR 4000 has to be connected. With the X-ADAT, an FPGA was soldered directly onto the board, and if you look at the Xtante expansion board, a board was simply soldered as a piggyback. I like the Xtante solution because it requires the least effort. In my last video, we developed our own control board for the Class-D amplifier, but the effort was quite high. Well, simplicity wins here. In addition to the WiDAR 4000, I would like to add an Ethernet connection for the controller, a small OLED display and an SD card holder, and some expansion headers, because I don't know yet what I will do with the system later on. My wife also thought it would be a cool idea to be able to control LEDs on the stage directly from this console, so we are also planning an RS485 IC and a socket for outputting DMX512 signals. If everything goes well, our X32 will become a Behringer X64 Grandma Lighting version 4. But first of all, we now need to specify the basic dimensions of the circuit board and position the connection to the X32 correctly. Now we put all the components we want to use on the circuit diagram. In addition to the connections, this also includes a 3.3 volt voltage converter. As I want to use the USB connection of the WiDAR 4000 without opening the X32, only one direction of this board remains. So we place the WiDAR 4000, the SD card and the XLR connector before we route the tracks. As with the original boards, I provided a ground plane on the left and right to ensure good grounding between the housing of the mixing console and the expansion card. I took a bit of risk with this project. I actually had the board manufactured without even looking at all the protocols. Since we can freely assign all lines in the FPGA, I'm fully relying on this flexibility at this point, in case my offline reverse engineering of the board is not correct. My final goal would be to use the X-Live controls in the X32 to select individual MP3 files on the SD card, but the minimum goal is to receive and return audio data from and to the X32 in the first place. We therefore need the functions of the XUF or XUSB and then later on those of the X-Live. Unfortunately, it is only possible to view the individual signals when the card is installed. So I have to solder test jump wires to the card and install it inside the X32. I prefer to use my X32 core here. In the case that I break something, the damage won't be as bad as with the full-size console. So solder on the test leads. Here we need the 2 control lines and a ground connection in any case. The 4 I2S or TDM-like signals would be a good idea if they are such signals at all. The X32 displays the name of the respective card. Since the Schematic U-Track32 does not display its own name, it is probably not the name that is transmitted in plain ASCII, but some kind of ID that the X32 can then retrieve from its firmware. To get an idea, I first look at the 2 communication lines over a longer period of time when the console is switched on. Since I couldn't find any documentation about the cards on the internet, I have no starting point here. For inter-process communication between my own controllers, I always use either UART, I2C or another basic communication type. Hopefully this will be the case here too. If they are using some kind of encryption, this project will have a hard landing. So I started with classic UART and looked at the supposed RX and TX lines to the STM32. These are the resistors R59 and R102 on the X-Live. I then tried out the bitrate and coding for RS232 in the scope and changed some settings. And indeed, at 38.4 kilobaud, I was able to find meaningful hex codes that also corresponds to readable ASCII characters. After a few reboots of the console, I was also able to find the desired init commands for the expansion card. And what can I say? Even the name is transmitted as plain text command. Great! This means I can fool the X32 into thinking it has any known expansion card, whether X-ADAT, X-USB, X-Live. Everything else was then painstaking work. I then spent over an hour sending various commands from the X32 edit software to the SD card controller and writing down the various commands. In total, I was able to track about 20 commands with matching responses. Here you can see, for example, the commands for listing the individual tracks on the SD card, and here the current position, which is sent from the card every 85 milliseconds as status information while playing some audio. I then forked my FPGA audio player GitHub project as a starting base for our new project and implemented a subroutine for the X32 communication in the SAMD21 code. At least basic communication between our new DIY card and the X32 system should now be possible. However, we are still missing the audio data. Without any further information, it's already a good approach to assume classic digital and uncompressed signals here. The UltraNet also uses a typical audio connection, so I once again connected additional test lines to the resistors R89, presumably one of the 4 audio signals, R100 and R101, which are lying next to each other and looking quite promising. To get an audio signal to the card, let's connect a stage box to the console and see what happens. We seem to have 3 different clock rates here on the 3 signals. A slow signal, a fast but steady signal, and one with a repeating pattern. Could be audio data. The fast clock signal has a period around 80 nanoseconds, which probably corresponds to a common 12.288 MHz signal. We know that the console works internally with 24 bits, but if we count the individual bits here, we end up with 32 bits. 12.288 MHz divided by 32 and we end up with 384 kHz, and since the console works internally in blocks of 8, we finally end up with 48 kHz per channel. Great! That's the expected audio clock. Yeah, we have audio signals that we can use with our Wider 4000 now. As there are no frame sync and bit clock signals for the 4 return channels to the X32, these signals should take the main clocks of the console directly as a reference and transmit the bits back synchronously. As we now can use the basic concept of I2S protocol, the effort to receive 8 TDM-based audio channels is doable. Receiving is synchronized to the frame sync and the individual bits are read out with a bit clock. The rest of the system is based on the UltraNet mixer or FPGA audio player that I uploaded to GitHub. So in theory, we should be able to play MP3 files from the ESP32 via I2S and feed it back to the X32. In addition, we can read out individual TDM channels as 24-bit vectors, mix them within the Vido 4000, apply EQs, gates, compressors, and send it back as a stereo signal to the aux channels of the X32. And with this solution, we should be able to mix 32 channels within the main console, mix 32 channels within the Vido 4000, and return them to the aux channels of the X32. This gives us in total 68 channels that we can use. And finally, MP3 playback on the X32. Well, my wife asked me why I would not use a regular MP3 player. She has ideas. Come on, we have to solder circuit boards now. Okay, everything seems to fit mechanically and the board sits well on the X32 housing. The small carrier board for the Vido 4000 PCI Express connection also fits well, and the height of the whole construction also fits into the expansion slot. Great. The audio mixer from my guitar project already has all the necessary functions on the board. Reading multi-channel TDM, a multi-channel audio mixer and some EQs. Only sending of TDM is not yet available, but based on the TDM receiver block, we can set up a TDM transmitter for 8 channels with minimal changes. To do this, I first define the output vectors as input vectors and the serial output signal. Then the receiver section must be removed. The individual bits are then set on each falling edge so that they can be read on the rising edge from the X32. According to the TDM definition, the first channel begins on the rising edge of the frame sync signal. Then the second channel begins after 32 bits and so on. After all 24 bits have been written, we have to transfer another 8 bits with the value 0 to complete the 32 bits per channel. This is how the X32 should actually understand our audio data. Before I can test the new board with my X32, I first have to install all the firmwares in the individual controllers here. And yeah, maybe it's a good idea to do a dry run on the USB connection without the X32 connected to see if all chips are communicating with each other and if the Ethernet jack is working and the SPI bus, I2C bus and so on. Yeah, for this I have to compile the Quartus project first and then upload the SAMD firmware together with the bitstream for the FPGA. So let's go. So first we have to compile the Quartus project. Now I have to convert our bitstream file to a header file for the Arduino IDE. For this I'm opening my project here and update the FPGA bitstream here and let's have a look. Yeah, looking good. Okay, so now grab from my other screen the Arduino IDE, the SAMD, and check if the bitstream is updated. Bitstream is here. Yes, it's looking good. So compile. And now the first time I will connect this to the computer. I hope it is working. We'll see. Grab a USB cable and plug it in. Yeah, this is a good sign. Upload to the port of this device, so COM7, and upload. So far so good. Now we have to upload the code to the ESP32. And to upload our code, we have to set the SAMD21 to firmware update mode so that it passes all serial communication to the ESP32. So I'm using the command for here, echo SAMD update Nina to COM7. Yes, the LED is now blinking a bit faster, and upload the Nina firmware. Okay, so let's check if we can communicate with our three devices, and I've implemented a very simple command for this. It is leaned on the SCPI command protocol for laboratory devices. It is *IDN ? And for this I will connect with the Linux tool Minicom. So let's see if we can communicate with the first device. It's the SAMD21, which owns the USB connection. So SAMD IDN ? Yes, DN. SAMD IDN. And yes, it's answering. It's X-FBAPE USB control version 3. Great. And now I'm entering the same command, but without the SAMD. And then it is directed further to the Nina module. So *IDN ? And we have X-FBAPE main control version 3. That's really great. And now check the version number of the FPGA. FPGA *IDN ? Wonderful! X-FBAPE FPGA version 1.08. But before I connect this to my X32, I will connect a laboratory supply to see if the 5-volt rail is not drawing too much current and will damage my X32. So if it is around 200 to 500 milliamps, I think that's fine. So limiting to 5 volt and a current of 500 milliamps. And it is starting, and it is drawing 0.2 amps. So let's connect to the X32 and see what happens. Okay, we have voltage. The LEDs are on. And the X32 is still alive. Great, woo! Okay. Setup, card. Oh, come on, no card installed. Why? Obviously, there's a card installed. Okay, so we have to do a bit more digging here. There are several more communication lines on the original PCB I did not check. I was hoping that the UART connection and the TDM connections are enough, but doesn't seem so. So first I have to disable everything, remove the card and plug the other card and do a bit more digging on the other signals and see if it is then working. Looking at my handwritten schematics or notes here about the original X-Live card, I see that there are two types of used resistors, 100 ohm and 330 ohm. And if I see this correctly, 100 ohm for receiving and 330 for sending. 3.3 volt divided by 330 ohm results in 10 milliamps. So this is quite safe for the X32. Resistor R99 has a 330 ohm. And up to now I did not have a look at this signal, and so I will check this line with my oscilloscope, maybe another communication channel. And it triggered and it stays high, so it's only a card enabled signal. Okay, so that's quite easy to implement in our code. So we have to hook up in Quartus and set the signal to high. Okay, so I changed the code a bit and the initialization routine is a bit different now. So we are starting with a *8BE hashtag, then we are waiting 6 seconds as we have seen in the scope. Then I'm sending this large string here and then wait a bit and then send the *8BE hashtag again and then wait 1.7 seconds and then I rise the reset signal. So let's see if this is working. Start the X32 and go to single shot mode. Okay, and here we have some information. So zoom in to this. Okay, *8BE hashtag, that's fine. That is what we are sending. And then the X32 is sending something. star8r hashtag. Okay, it requests some information from us, but we are not sending. Why? And then what is here? Ah, the very long initialization command. Okay, the communication seems to work, but we are not answering. So maybe the delay is a bit too long. So let's reduce this 6 seconds. Let's try 1 second and 500 milliseconds. Something I'm just choosing here. Then upload the new firmware. So connect the Vido 4000 and upload. In the meantime, we can have a look in the X32 edit. Connect. Okay, so still no card there. And then restart. So go to the scope again. Start. Okay, there's a bit more communication now. That's probably a good sign. So have a look here at the first command. Oh yeah, that's looking good. That's promising. Star8r hashtag, and we are sending. Okay, I cannot read that here because the time resolution is too bad. So could it be that? Try reconnect. There's a green sign. There's a green sign. That's it. That's it. Here is it. Yeah. Okay. 5 hours. It took me 5 hours to hear. Okay, great. Unbelievable. I made it. Okay, so now I can change parameters here in the X32 edit, and I can have a look at our terminal program. And then we can see if we can manage some commands here. Okay, and we will have a look at the communication here in the scope parallel. So I'm choosing the yellow curve. Okay, so here we can see everything, and here I can change the parameters for the X32. And here I have to log into my terminal. So we enable the debug interface, SAMD, debug X32 at 1. Okay, so now we should see all commands the X32 is sending. So I'm selecting 16 channels. Oh, great. Haha. It's working. So the X32 sends us several things. Some new commands, I think. And obviously we sent something the X32 was not expecting. There was a system error. I never saw this message before. But anyway, he detected 2 SD cards now with 32 GB. I think I put some fake cards here. Yeah, great. Ah, okay. Check calculation, yeah, obviously correct. System error 14, okay. So here we have a bit more work to optimize the communication. But now let's go to the control of the recorder. And let's see if we can select between SD card and USB interface. So if I click on USB, great, it's working. It's working. Star8C80U hashtag, so for USB. And now I go to SD card, then we should switch to a C here. Yep, that's correct. That's fine. Play. Okay, he started playing. Recording, okay, it's recording. We get a file name here, great. So I stop the recording. That's fine, start again. So we are recording with 32 channels. We are seeing here in the command 320 hashtag, and I go to 16 channels. And now we see here a C16O hashtag. Oh, the C is only from the time index, but 16O hashtag, that's fine. Go to 8 channels and 080 hashtag. So great, we have several options to make a communication between the X-Edit and our own card. So that's really great.
He's with us, Jesus for us. Hallelujah, hallelujah. We give praises to Jesus. Oh yeah.
A couple of days have passed since my last work on this project because I had to record a gospel choir here in the region where I'm living, and I was really glad that my X32 is still alive and I could do the recording. But back to our project, I connected a microphone here to my stage box, which is connected over AES50 to my X32, and I'm feeding back the processed signal to the stage box and then to my audio interface to record. And I'd like to test my audio processing in my own card. So first let's try the general processing. Okay, now you should hear me through the microphone, so that's still working, that's great. And now I'm changing the routing and get down with the voltage a bit.
Okay, this seems not to work. Okay,
yeah, as you can see here in the X32 edit, all signals of all 8 channels are at 0 dBFS, so we have a lot of disturbances here. Maybe a bit shift in the signal we are receiving, I don't know, maybe the transmitter. To test the overall signal quality in my board I made, I will connect the input in my FPGA with the output directly to see if the serial data can pass through the FPGA without any problems. And if we get then clean signals, I have to work on the TDM decoder and encoder. So go to Quartus, recompile it with a feed forward of the TDM data and then see if it is working. Okay, the software is updated. I go to the X32, this is still working. Okay, and then enable play. And yes, okay, it's working here. That's a good sign. And we can test our TDM encoder and decoder if there's a bug. As you can see here, I connect a test signal to channel 2. This test signal is based on a direct digital frequency synthesis and is creating a sine wave with a specific frequency, and I only wanted to test if the TDM sender is okay with the right channels and is okay with a different signal than the input signals from the X32. So it's connected to channel 2 and we should hear a sine wave on this channel. The code is online and still the internal processing, of course, is working. I did not change anything here. So go to play. Okay, yeah. I think it's working. I hear a bit more hiss and it is a bit louder. This is record, this is play. So there's something wrong with the gain, but I did not program any gain. So maybe I have a problem with some bit shifting here. I'm not detecting it. You can see here, there is noise increasing between channel 4, 3, okay, 2 is our sine wave, and 1 there is, okay, there's some hiss here. So this is the background noise, and I think I do a mistake here in placing the bits in the right position. But let's see if we can get the sine wave. Yeah, it's working, great. I think we have the base for an own digital mixing console within a digital mixing console. Cool. So all we have to program is some kind of volume control and then we are fine. To test the system, I connected my volume control to channel 1 and channel 2. The SD card playback, which is still not working at the moment, on channel 3 and 4, and the Bluetooth to channel 5 and 6. And in channel 8 we have our sine wave test signal. And let's see if it is working. Go to play. Okay, the sine wave is there, but we have nothing on channel 1 and 2. There is no volume here. So I have to change the volume in the FPGA. Mixer volume main at 0. And we are receiving the microphone on channel 6, so I have to increase the volume here too. Mixer, volume, channel 6 at 0. Mixer, balance, channel 6 at 50.
And then, yeah, we have the center. Ah, unbelievable. This is working freaking awesome. Yeah, that's it. We have a full 32 mixer inside our 32 channel mixer.
Okay, a terminal program is quite cool to use, but it is not very convenient to change the volumes of channels. So I programmed some small user interface here, and we can test if this is working. I already tested this, but I wanted to show you the volume.
The volume can go up and down, so we can even boost up above 6 dB. And I'd like to show that the EQs are working. So I go to equalizers, go to, for example, a peak filter, change the frequency, and now it is working. So the signals are a bit brighter, you can hear it now here, or with more volume in the bass. A low-pass filter or a high-pass filter. And then we can have a look at the dynamics. I go to a limiter, for example, and increase the makeup and decrease the threshold to minus 40 dB and increase the hold time a bit and make it a bit faster here and maybe increase a bit more. And yeah, we have a limiter here. And I can shout or I can whisper.
After a few adjustments, MP3 playback from the SD card and the Wi-Fi interface are working now. I have adapted the web interface of my audio player to the additional channels of the X32. This means that you can set the individual channels and also play the MP3s via the web interface. The EQs can be adjusted in this way too. Of course, the Windows software can be used as well. As I promised, I implemented DMX512 directly in VHDL. Originally, I planned to use the ESP32, but the 9er module of the WiDAR 4000 has a few limitations here, and configuring a third UART in addition to SPI and I2C didn't work for me. To set individual channels, you can either send a short command via USB or transmit the new values via Ethernet. I am also considering implementing the X-Touch protocol as a useful extension to the overall system. I've already implemented the protocol used for this device in the PC dimmer software for lighting control and only need to port it to the SEMD21. I still have enough space in this controller. Then you can mix the additional 32 audio channels directly via Ethernet with real faders. The Arduino WiDAR 4000 also only has a fairly small FPGA with only 16,000 logic elements. You could use a larger, but of course more expensive FPGA here in order to use more EQs and other audio functions. Many things are already prepared within the code. But regarding to digital or analog audio outputs and of course inputs, we have no significant limitation here, and the DIY expansion card could do much more here without big effort. One final word. I can't promise that there will be another major project like this in the next video, but there are still many things that can be done with this technology. A port to the Behringer Wing is also doable now, and if someone borrows me a console, I'd be happy to take a look at it. Well, that's it for now and see you next time.